You know, history makes liars of us all. And you're right, that was the thinking. When networks were unreliable, TCP kind of added strength to it, but if networks were basically reliable, things were fine. And then we put the internet on mobile phones. And the loss rate, at least initially, was awesome. It was one of the few systems that had a loss rate of 1 in every 10 packets never made it. It was pretty bad. And do you know what collapsed? TCP.
You're listening to Ping, a podcast by APNIC discussing all things related to measuring the internet. I'm your host, George Michelson. This time, I'm talking again to Geoff Huston from APNIC Labs in his regular monthly spot on Ping. A lot of Geoff's experimental measurement system is looking at behaviours in the DNS. Geoff has noticed that for the huge, multi-million unique DNS queries that he generates in clients that are coming back to the APNIC Labs DNS servers, an astonishingly high number are retransmissions. In fact, it's virtually double the expected query load. For 150 million unique DNS labels that Geoff generates that will never be seen by another client, he's seeing 270 million DNS queries. Many of them are an almost immediate repeat. That is a lot of repeated traffic. What's going on? Is this an instance of the tragedy of the commons, or is it simply a fact of life in the modern internet? Geoff, welcome back to Ping. What should we talk about this time?
Hi, George. No, it's a pleasure to be back. I'm just actually back from a tiny bit of travel, and I went to a couple of meetings where the DNS was on the agenda. I was at a meeting of the Operations and Research Group, DNSOARC, and later on the following week I went to a meeting of the sister RIR organisation of APNIC, the RIPE organisation, which had their meeting also in Edinburgh, and there was a DNS session there too. And I want to talk about things DNS, but...
Right, let's do it. DNS it is.
A little bit of economics. Do you know about the tragedy of the commons?
Well, you know, it's a phrase that I think everyone's very familiar with, but knowing a phrase and understanding exactly what it means is kind of subtly different. So why don't you give me a rundown?
Well, it's kind of works on the theory. The commons were evidently, I wasn't around and neither was anyone else, dear listener, an aspect of medieval England where a collection of houses, a village, would have a common area that nobody owned and that everyone could graze their animals.
So nobody owned it, but everybody shared it.
Shared it. They could use it without charge. It wasn't anybody's land. It was everyone's land. It was the commons. And the problem was it only worked if everyone was restrained in the number of beasts they set out on the commons going, eat grass. Because as soon as someone got greedy and sent out, more, the place just went to rack and ruin because all the grass got eaten, it turned to mud, bad things happened. And it actually led to, according to the economists who studied this, a subsequent move of the fencing of the commons to try and sort of, if you privatised it, people would look after it better. But there's a generic kind of principle about unconstrained human behaviour.
Yeah.
Free resources tend to get exploited to the point of overconsumption and degradation.
It feels a little bit like a version of the prisoner's dilemma, that the only good answer in the prisoner's dilemma is for them both to do the thing that's mutually beneficial. And if either one of them tries to get their own safety secured, it stuffs up the whole thing. The commons, everybody's got to be a good player. And the minute there's one bad apple that takes more than their free rights, the whole thing goes to pot.
So, free resources get abused. They just do. Free money. Free whatever. And so there's this aspect of this applied to the internet's domain name system.
Well, I'm not paying for it, so there's a quality that makes it feel to me very free.
Well, if I run an authoritative server where I answer queries that other users have made, so if you want to know about potteroo.net, it's my server that's on the hook. Does anyone pay me?
So answer here means specifically be the authoritative answer, because there might be many other DNS players along the path who feel like they are, air quotes, providing the answer, but ultimately somebody has to have asked you, Geoff, in order for that to happen.
Right. Someone needs to have sort of seeded the DNS with the original sets of, data. And that's actually an act that doesn't get compensated by the people who actually are making the queries. Queries are free. And if you observe from that, well, do people over-query because they're free? That's a really interesting question.
Yeah.
You see, the DNS works and it's really efficient because it uses the UDP protocol, the datagram protocol, the protocol that says every packet is an adventure. If I send you a UDP data packet, you may or may not get it. UDP doesn't care. You see, this actually, oddly enough, and let me digress a tiny little bit, was actually one of the issues with the early forays into packet networking in the 1960s. We had been used to a form of networking which, when we moved from analog to digital signals, we regarded the signal we were switching, even digital, as a consistent stream of packets. And we ended up switching the most incredibly expensive thing we could possibly switch, time. So that if you had a common resource switched between, say, 8 people, for the first eighth of a second, it was user A, and then the next eighth, user B, etc. In other words, you tried to sort of fair share amongst competing people by actually switching on a common view of the time, which is interesting. But what it meant was that the network was carrying the integrity of the conversations. It didn't matter how clever or dumb you were when you attached your speaker and microphone to this network. The network itself would preserve that digital data as it switched it through the system, circuit switch systems. When we went to packetization, there was a debate, and it was a furious debate. The debate was, in a packet switch network, the packets don't go all the way from A to B. It's actually a series of hops. There are intermediate switches. And so you eat the first switch that then passes it to the second switch, then the third, then the fourth. Now, it doesn't really matter how you define the sequence of switches, whether it's predetermined, whether it's, like the internet dynamically discovered, doesn't really matter. But the issue is, when one intermediate system hands a packet to the next intermediate system, does it care that the next one received it? Ooh, big question. Because if you care, X25, then you actually get a whole sequence of A sends it to B, B acts it back to A. B sends it to C, C acts it back to A. What does this mean? Well, if someone pops a packet in to this system, it will either come out really reliably, or the interior of the network will go, oh my God, all hope is lost. Let me destroy the circuit. Let me give you an indication of failure.
Because every hop along the path, people are saying, did you get it? And the person on the other end is saying, no, in which case you have the burden to retransmit it. So bounded in time, it's going to get there, or the whole thing's going to say, we've got a problem.
Right. So X25-based networks, which were really popular for a small window of time in the 1980s, worked on this principle of reliable hop-by-hop transmission. One of the networks that I did work on, DECnet, had a venerable protocol called DDCMP, and it was actually the same kind of thing. All the intermediate systems effectively explicitly acknowledged successful receipt of a packet. And so the thing injecting packets didn't have to care. Once you passed the packet to the network, you could assume that it was going to come out the other end. What you couldn't assume was speed, because, if someone had stuffed it up, they'd sit there and try for quite some time before they gave up on the entire conversation.
So if we bring this back to an internet context and the idea of internet protocol, the actual packets that are the internet protocol packets, whether they be 4 or 6, they're kind of stuck in the weeds on this. They're not saying absolutely must be on a network like DDCMP or X25. They're actually saying, don't care what I run on. Piece of string, giant fiber optic, 100 gigabit channel, totally up to you. I'm just a packet, mate.
Well, that was the genius, and I will say, of the internet, that looking at everyone else who was busy doing reliable reliable switching and effectively synthesizing a circuit out of these hop-by-hop packet elements, the internet said, nah, every packet is an adventure. It's not the network's problem to identify and fix it.
I think every packet is an adventure needs to be on a T-shirt. I think that's brilliant.
That's right. We're off on a big adventure. Some of us might not make it. Oops. And that was kind of it. The argument was, and it got encapsulated in what we call the end-to-end principle, that it was left to the two machines at either end who were communicating to figure out if any packets hadn't made it and repair the damage.
Right.
And you kind of go, well, that was just IP. And you go, well, no, that was Ethernet.
No.
It was Ethernet. It was a whole generation of successor data protocol, designs that effectively said, well, this is a packet system. I don't actually care about the reliability of the packets. That's up to the communicating systems at either end. All I care about is just pushing it through. And if I fail, let's just move on with our lives, right?
So we don't actually routinely construct applications and services into IP packets. We've got a layering model, and there's a choice moment coming, which I think brings us back to DNS and UDP. How do you make something on top of this have the behaviors you need to know, is this unreliable or reliable?
Yes, a lot of stuff use TCP, this reliable transport. Now, TCP has overheads because there's no network state, but there really is state at either end. Instead of I to send you a packet, I have to go through a dance. Hi, George, I've got a number. Here's the number I'm thinking. The packet is going to be called a synchronized packet, so it's a SYN.
Hi, Geoff. Here's an ACK for that. And by the way, here's a number I made up that is my number that you should remember when I tell you things.
Ah, George, I see you've received my packet and sent my number back to me, and I've got your number. Let me acknowledge your number. This is the third part of the three-way handshake. And now we both have sequencing numbers that the other's using.
Terribly polite protocol, isn't it, Geoff? So polite. Oh, thank you for sending me that packet.
Yes. Oh, thank you. Here's my first data packet. Now, I know I said magic number 10. Well, it's got 10 bytes in it. So the new magic number will be 20.
Thank you, Geoff. I got that magic number 20. Here's my answer with magic number 2.
Ah, I see that you've received magic number 20. I will delete my copy because you have it. I don't need to resend it. Thank you, George. Oh, and by the way, let me acknowledge 2. You see how it kind of moves, that instead of doing hop by hop, did you get it? Did you get it? Did you get it? The two end systems play the did you get it dance by advancing their respective sequence numbers. The cost, well, it's a three-way handshake to start with.
So there's a bit of delay coming in.
This whole thing about let's exchange sequence numbers works perfectly fine if we've got stuff to say to each other. But George, I only wanted to say hi.
Short conversation.
That's 2 characters. That's 2 bytes. So it's kind of SYN, SYNAC, ACK, hi, ACK, FIN, FINAC, FIN. That's a lot of packets to go hi.
Hi, yeah.
And when the approach came to think about implementing the domain name system and its resolution as an internet protocol, it was very quickly realized that there were many, many points of conversation, many points of authority, potentially. But each conversation would be tiny. Hi, do you know about www.apnic.net?
No.
Done. That's it. I don't need handshake, blah, blah, blah. It's just, fine, tell me yes or no. I don't care.
I think tied up in this is sort of a subsidiary story that if we were talking about a medium that was so atrociously noisy, 1 packet in 2 never got through, you might be very uncomfortable with that class of behavior. But we are living in a world where the behavior assumption was most packets get through. And you'll need to say, I didn't get that, or you'll need as a sender to say, looks like you didn't get that, I think I'll do it again, is kind of down in the threshold where you're not really paranoid about checking every single time. It mostly works.
History makes liars of us all. And you're right, that was the thinking. When networks were unreliable, TCP kind of added strength to it, but if networks were basically reliable, things were fine. And then we put the internet on mobile phones. And the loss rate, at least initially, was awesome. It was one of the few systems that had a loss rate of 1 in every 10 packets never made it.
Wow.
It was pretty bad. And do you know what collapsed? TCP.
Seriously?
Because if the loss rate is high enough, it never gets, I suppose, what I'd call a full head of steam. It always just sputters. Hi, here's one packet. Because the way TCP works is that if you send me an ACK for a packet, I'm going, well, that's fine. Here's 2 packets. And you send me ACKs for those, and I go, well, George, this is cooking. Here's 4.
I'll ACK that.
8, 16.
I'll ACK that.
TCP has this system, which ironically is called slow start, which is anything but.
Yeah.
It's actually exponential start, and it just zooms forward. If I've got a lot to say, TCP works brilliantly as long as the loss rate isn't bad. If the loss rate's around 2-3% max, TCP is okay.
Because you get the second part of the TCP behavior, which is under loss. The back off is extreme.
Oh, it's very extreme. It's kind of, a packet loss, panic, ring the fire alarms, ring the bell. Let's back right off. And so, oddly enough, you might have thought the TCP was sort of perfect for crappy networks. It's actually very imperfect. And what actually became really quite neat was UDP, because applications expected damage. It's kind of, lost a packet. It's not a big drama. And UDP was always intended for short transactions. Although some people abused it and started doing weird and wacko things using gigabytes of data over UDP, but they were loonies.
Well, they were loonies then, Geoff, but if we look at modern parlance and quick, using UDP for megabytes of data has come back into fashion. But we've drifted slightly here. The point is, UDP was the way to say, I'm not going to invest in a layer to do all of that reliability checking for me. I'm going to fling packets out with the least overhead, particularly when I'm asking questions like DNS questions. What's the address of this name?
Single packet question, single packet answer. And if packets get damaged, it's left to the DNS application to figure it out and ask again somewhere else.
Now you just said ask again.
Well, yes, because if you don't get an answer, what are you meant to do? Go and sulk? I'm sorry you didn't get an answer. Nobody likes me. It doesn't work like that.
It's not the EOR network, is it?
Oh, absolutely not. I need an answer. I'm going to get one. I'm going to keep on asking till I get one. And so it's persisted under loss, right? Because that's the way we designed it. The application has to sort of make up for a network that isn't perfect, okay?
Right.
Now, I said before, queries are free. So when do you re-query?
Now, I'm a good person, Geoff. I want to go to internet heaven. So I'm going to say the right thing to do is to re-query when you're really sure you have to and not re-query any other time. There you go. I'm a good player in the commons.
Well, you've also read RFC 1536 that said you'll wait for about 5 seconds.
That's a long time.
Oh, continents have drifted in 5 seconds, Attention span, entire generations of attention spans have come and gone.
Squirrel.
Exactly. But that was the advice, be patient, wait, don't splutter packets into the network. And of course, since then, the networks have got bigger, but at the same time, we have got way more impatient. We are extremely impatient about this. And so what's the best way to get an answer quickly?
Vincent twice.
Well, ask.
Are you there yet? Are we there yet? Are we there yet? Are we there yet?
Yeah, I want to drive from Canberra to Sydney. Okay, how do I get there faster?
Are we there yet?
Send 5 cars. But I'm only in one of them. Sometimes it doesn't work.
That's the Million Man Month statement about you can get a baby in under 9 months if you get 9 women to carry a baby, isn't it?
That's the same kind of fallacy. But oddly enough, in the DNS, it's not quite a fallacy. You see,
what?
Well, the thing is, if this stuff is unreliable, and let's go to our magic 10%, then 10% of the time, I'm not going to get an answer, but I'm going to wait for 5 seconds. So 10% of folk will have a 5-second delay, and they'll ask again. 10% of them will not get an answer for another 5 seconds. So 1% of folk will be waiting for at least 10 seconds for an answer, and 10% of them won't get it, etc., etc.
Well, in a network of 2 billion users, 1% is an astronomically large number.
Well, it is. And the whole issue comes that maybe that's the wrong strategy.
Yeah.
So one thing you can do is not wait 5 seconds. I will work out reasonable approximation is for when you should respond. A packet can circle around the globe in a second. In fact, you can do it in half a second if you're lucky and on, the right pieces of cable. So I'll wait for a second because if you haven't answered it.
Yeah.
In fact, damn it, 300 milliseconds.
You know what? I would feel like this was still in the class of good behaviour in the commons. If you're genuinely likely to get an answer sooner than that, waiting 300 feels like a pretty good fit for human-centric delay, the experience of waiting for a thing to happen, and the reality sometimes you have to do it again. I could be happy in that world, and I'd love to believe it's another short episode and you're telling me you went out and looked and that's exactly what you saw because we're good citizens in the commons of the DNS. That's true, isn't it, Geoff?
I'm sorry. Yeah, right. So we went and looked. We went and looked for a day using this ad-based experiment, and we sent out a large number of names. Oddly enough, because we don't want caching to happen in the DNS, which glosses over everything. All these names are unique, but that's easy. You just make a long name and, add some variable fields every time. So on this day, we did 150 million unique names that got asked for by users. And they're unique. And they're unique in a couple of ways. One, the name only exists just once in time. That's it. Secondly, the only systems that can answer that DNS query are ones we run. So we see the query because we're the only people that are authoritative and no one can cache it because it's unique.
You kind of brought the cache word to the table, and I think we're probably going to want to come back and talk about that in another episode because there is so much in cache. Cache is fascinating.
If it wasn't for the cache, there wouldn't be the DNS, but that's a talk for a different day.
But the thing is, you've constructed a world with lots of unique labels where caching simply can't apply because they've never existed in the system before.
Yep, 150 million of them in 24 hours. We were very busy.
Good-sized experiment.
Decent, all over the planet. But we received 250 million, in fact, 270 million actual queries. So 150 million becomes 270 million in the DNS.
Well, it's not quite double, but it's a hell of a lot closer to double than a small percentage are repeated. That's most queries are repeated, Geoff.
On average, most queries are repeated. On average, the DNS is going, to be sure. And on average, it's sending out the query a second time. Now, one theory is the internet's far worse than anyone ever suspected. They've all waited their obligatory 300 milliseconds or whatever their timeout might be. They haven't got an answer in time and they're re-querying.
Well, I just want to put my hand up here and say we're recording this using a system that is transmitting live audio and video and effectively is like a 200 to 300 kilobit stream continuously from me to you and you to me. And if the level of behavior in that system demanded every single packet that we are doing was sent twice, I'm fairly comfortable we'd be seeing artifacts like delay or breakup on this video, Geoff. That's what we used to see in old noisy systems when things could not reliably get data through. So if you and me can reliably send hundreds of kilobits of data to do this video and audio recording, I'm not buying that the DNS is suffering a noisy network and has to retransmit. You've just said it is retransmitting, but you haven't said it had to do it.
Well, we go a bit further because we're seeing all these queries. And so what we actually do is then go, well, a duplicate query has the same query name, A.B.C, and the same query type, A record, quad A, whatever, because we've got a recording of every query we see. Why don't we time the interval between the first query and the duplicate query? Why don't we actually see how long people are waiting? How patient?
That's quite interesting. So you don't actually need their clock. You just have to have your own clock recording the interval between seeing it once and seeing it again.
Well, I just record the time when I see a query. Go back over the logs and go, well, that was the duplicate of the first query. What's the time difference between the first and the second?
And if you're using a system like DNS cap or TCP dump PCAPs, you actually automatically get a packet timer, don't you? An arrival time, which means you can do the packet interval either from a log or from a data stream.
PCAPs is an extraordinary amount of data to wade through. I'm using logs. It's good enough for this jazz. So, the log says, here's a time interval between queries. And we've said before, this is not timeout. This is not a crappy network. So what sort of time interval do people like to do? Because, as I said, half of all the traffic we see, almost half, are duplicates. So of the duplicates, just looking at the ones that weren't the first, but it's a query that happened before, right?
Yeah.
45% of all those duplicates come to us within 10 milliseconds of the original. Oh my God!
Just before we drill down there, this is quite a skewed distribution, isn't it? I mean, a small number of these duplicates probably arrive a significant time after, like more than 300 milliseconds, yeah?
Well, a small number might well be the first time didn't make it. I'm twiddling my thumbs and I'm doing a DNS timeout and I'm trying again.
Real loss.
Real loss will cause retransmission.
Now to come back to the astonishment moment, almost half of the retransmitted packets are 10 milliseconds or less.
Less.
Holy cow, Geoff. Holy cow.
Well, let's up the clock a little bit and go 20 milliseconds. 20 thousandths of a second. 200ths of a second. That's not a timeout.
No.
65% of all queries occur almost like we'd say tap, tap. And it's the same query.
I am astounded, Geoff. I mean, to me, that shrieks deliberately coded.
Okay, so let's dig a little deeper because it's always fun to dig a little deeper. Do you know about happy eyeballs, dear listeners? And George, maybe folk do that.
I've got a kind of vague feel. It's an odd thing, isn't it? It's this idea that we need to construct a way to handle how do we make 6 happen if 4 and 6 both exist. It's in that space, isn't it?
It's in that space. And it used to be when I'm opening up a TCP session that a Linux operating system would wait for 108 seconds before saying that's not going to work. So if you didn't know if you could open it using V4 or V6 and you tried in, say, V4, the TCP part of the operating system would say, hang on, working on this, 3-way handshake, leave it to me. Oh, that SYN didn't make it. Let me time out and try again. Oh, that SYN didn't make it. And it'd take 108 seconds to go, I don't think it's working. Let's try V6.
I have a story for you from the deep, dark days of the early internet when people still used a file called hosts.txt. And it took so long to serially check line by line that file to find where I was coming from that when I used the protocol called FTP to try and download code from London, getting it from a machine at the University of Maryland, the 30-second timer on the login would time out and disconnect me before it had worked out who I was.
Steam-powered computers, George, they were wonderful. Turn off the steam. Go to electronics. Oh, you British. My apologies to all the British listeners. I didn't mean it. This whole idea, though, of duplicating became a technique where instead of waiting for conventional timers, you do try and speed up the process. So what we called happy eyeballs was you actually try a connection in V4, but impatiently. In fact, you do it in 6 first, and if that doesn't work, you do a rapid switch over to V4.
You kind of set
It's a 2-horse race.
2-horse race. It's not wait for one, then the other. You fire them off with a just little bit of an advantage.
You handicap the one you prefer. And if you kind of go, oh, well, if you've implemented both protocols over the same paths and it's roughly the same time, whoever you've handicapped will win the race. So I handicap 6. I send out the 2 horses at the same time. 6 has a slight favour. You'll make a V6 connection if you can, but you'll rapidly fall back to V4.
Right.
And so you go, that's good.
Putting this into the context of the DNS, I'd love to say, Geoff, it must be that you're measuring happy eyeballs then. That's where you're going, isn't it?
No, not really. I'm trying to find an explanation as to why almost 2/3 of all the duplicates occur within 20 milliseconds. Someone is doing this, bang, bang. And happy eyeballs is part of it because certainly in the DNS, if I kind of want to make sure, then testing V4 and V6 is not a bad strategy. But there's more to it than that. In theory, I'm meant to have names with multiple authoritative name servers. And if I want to increase the resilience, a very clever recursive resolver, one that's making the queries, would go, Geoff, I see you've got 4 name servers out there that can answer my question. Let me send the same question to all 4 at once. Queries are free. I'll just take the first one to answer.
Right, but Geoff, that wouldn't look like, if you air quote it, duplicates, unless you measured across the whole system, whereas you're at a single point from what you've been saying.
No, that's where the argument breaks down. So let's see what other clever things people do. One of them, which we have noticed in a number of ISPs, is they're not really sure about their own DNS infrastructure. So well, it's been in a dusty cupboard for 10 years. And there's a bit of mould and bit rot growing on the chassis. It might not be working.
The perversity of the internet, where you trust the remote party more than your own equipment that you bought and set up to run service.
Google's public DNS has an awesome reputation. Cloudflare's All One has an awesome reputation. So tell you what, let me send the query to one of these open resolvers and at the same time work diligently hard to resolve the name myself. If I get an answer from the open resolver, I'm done. Otherwise, I'll keep on working.
Yeah.
Not a bad strategy.
I could believe in this strategy, Geoff, but again...
You could believe it? That would account.
I bring back to the table, that would not in strict sense normally look like a duplicate to you, would it? Because you would see different originators asking you the same question.
Same name. A duplicate is the same name, not the same asker. So V4 and V6, if they're asking for the same name, are duplicates. Cloudflare or Google and my resolver are duplicates if they're asking for the same query type and the same query name.
Right. So this begins to sound like a possible collection of reasons you would see twice.
An optimization.
Yeah.
Send off 4 racehorses down different tracks. Whichever one comes back, I'll run with it. The V4 racehorse, the V6, the one to Google, the one to Cloudflare, the one to OpenDNS, whatever. Queries are free. Just send them all out. Take the first answer you get, you're done. Sounds good?
Mostly. Got a few if but maybes, but yeah, I could be there.
So 1/5 of all the duplicates come from the same IP address. Jaw-dropping moment.
Wait,
I'm sorry.
45% of all the duplicates are rapid fire.
Yes.
And 1/5 of the duplicates,
of the rapid fire duplicates, of the ones that are tap, come from the same IP address.
I'm not using 2 people to ask this question for me. I'm asking it twice. Wow.
What's your problem, George?
Sorry, what? Didn't hear you. What did you say?
Yeah, what? Sorry, what? Sorry, what? I'm in a groove. Look, sorry, what?
Entering the room as a tragedy of the commons, I'm sitting here, frankly, aghast, Geoff, because this is taking a service that is notionally free, but actually has a publicly distributed cost. It is not free to provide the DNS, either as an authority or as a public resolver. It's a cost. And it's a packet cost in terms of congestion on the wire. And you've just said to me there could be 2 or 3 or 4 or 10 duplications to get an answer from a system that we already agree is overwhelmingly reliable, even if you're using the UDP shout into the void protocol.
60% of the duplicates are only single duplicates. If I say 1 or 2 duplicates, so in other words, a total of 3 packets, I get up to 80%. So most of the time, it really is tap. And it's so bizarre. Not tap.
But isn't that an abuse of the system?
Well, from my selfish perspective, as the resolver, I just want the answer, dude, and I'm incredibly impatient. So someone else has the cost to bear. Tough on them.
Oh.
It's the tragedy of the commons all over again. And I'm sitting there going, wow, where is this? Well, we know where it is because we know who's asking.
Oh dear, name and shame time. That comes up so often in these measurements, doesn't it?
It does, but I'll be vague. I'll be general. The hotspots appear to be where there is, if you will, network infrastructure that may not be so crash hot. So oddly enough, the Indian subcontinent, including Bangladesh, we see a lot of duplicates. Double the rate coming out of the US and Europe. That doesn't mean the US and Europe don't have it. They do. But the rate is much higher in our servers that serve the Indian subcontinent, and oddly enough in China and Hong Kong in that area, where, again, the duplicate rate is pretty much double what we see in other parts of the world.
So China, we know, has a national strategic view of DNS in the context of internet, and it is extremely common for people to use intermediary devices because they can satisfy national delivery goals by buying legitimated systems that do the things the Chinese state considers necessary for safe internet. So for China, my spidey sense is saying this sounds like intermediaries.
It's hard to say, George, because in our experiment, we don't get to see what happened to start this off. We know an ad got placed in a browser. We know that. But we can't trace the DNS from that machine all the way through to the one machine we can see, the machine that is asking our server the question. So between the user and that final sort of hopping off point, it's all black to us. We can't tell. But it does strike me as amazing that almost one half of the DNS are ghost cars. They're nothing. They're not real. They're just duplicates. And most of those duplicates occur almost back to back with the original query. And so the answer set is going out to all of them, duplicate and original.
Yeah.
It's not as if I don't answer the duplicate if I already answered one.
No.
We answer everything.
I'm kind of wishing there was a facility in the packet of DNS under this condition of behavior that allowed a flag to be put in the question saying, this is the second time I've asked. Because the thing you don't know is the origination order of these two packets. You know the arrival order. You can't actually know which of the two was.
You can't tell, and I can't tell. But if it's the same IP address and all that's varied is the source port, does it matter which was the original?
No, not really. I mean, it's kind of irrelevant.
Exactly. So in some ways, the most bizarre behavior where it's almost as if the switch is duplicating packets. Now, that used to happen, and I remember seeing it in about 1990, that certain switches from a certain really cheap vendor decided that when life was tough, instead of really switching one packet, they'd turn one packet into two for free.
Because the world always gets better when you put more stuff on the network, right?
More packets equals more joy, you know. But those days, thankfully, have
every packet's an adventure, Geoff.
Even when it gets cloned. But, you know, they were cloned packets. These are point of difference. It's a DNS source port that's actually changed.
Wow, Geoff, this is really fascinating. I think you might need to move to other forms of experimentation, like doing packet trace on the client-side resolver to see if you can actually see two packet queries being initiated out of some system.
Oh, at some point we resort back to understanding which resolvers are doing this and understanding who runs them and actually dropping them a note saying, hi, we've noticed something rather bizarre about the DNS system you are running. Whose vendor's code are you using? What version is it? How have you customized it?
So, dear listener, if you happen to know the reason that this behavior is now ubiquitous in the global internet, Geoff would love to know.
Oh, I would love to know. So much of the internet happens without us looking. And even if you were running a system that did it, do you know? Nobody knows.
Oh, God, I wouldn't have a clue.
No one looks down at this detail. And quite frankly, even if you run an authoritative name server, trying to find these rapid duplicates, you've actually really got to look hard. And so you kind of wonder, George, what else is out there at the internet? It's complete slop. The only difference is no one's bothered looking for it.
Yeah.
You know, it's out there, just waiting to be uncovered.
Folks, there's a world of measurement out there. We should all be looking at this stuff. That's really fascinating, Geoff. You've written this one up on your blog?
It's coming up in the next couple of days. I'm just in the final process of crossing the I's, dotting the T's, or whatever you do with I's and T's.
By the time this one goes to air, I'm sure you'll have it online, so we'll include it in the webpage with it. That was really great, Geoff. Thanks.
Thanks, George. Cheers. Till next time.
If you've got a story or research to share here on Ping, why not get in contact by email to ping@apnic.net or via the APNIC social media channels. Also, remember the measurement@apnic.net mailing list on Orbit is there to discuss and share relevant collaborative opportunities, grants and funding opportunities, jobs or graduate placings, or to seek feedback from the community on your own measurement projects. Be sure to check out the APNIC website for all your resource and community needs. Until next time.